Good evening, everyone. This is Sean Kennedy from Southern Methodist University. I'm going to be reviewing my time series project for the spring of 2020 with Dr. Sadler. The project that I've chosen for this semester is directly impactful for the work that I do every day. Currently, we are in the process of analyzing credit card transaction data with the hopes of predicting key performance indicators for a wide variety of retail companies, one of which happens to be a large retailer in the pizza space. So without further ado, let's get into it. The first thing we want to address is the stationarity of the time series. The stationarity of this particular time series is non-existent. There are multiple components here that are exhibiting autoregressive behavior and cyclical behavior. You can clearly see from the variance or the violin plots here that the variance across days is wildly different, as are the means across days. That could be for a couple of reasons. One, behaviors could be different on weekdays, particularly Monday. But there's also a little bit of an anomaly with this data where some of the data collected on Saturday and Sunday could actually be flowing into Monday. So there's data cleanup there that we actually can't do because we don't get that data from the credit card providers. So we have to assume that it is real behavior, although potentially it's not as real as we think. The first model that we're going to look at is an ARUMA model. We're going to strip out our 7-day seasonal differences because we see the weekly trends, and then we're going to model the residuals. So after taking our 7th order difference, we're going to model an ARMA 5-7, which was the model favored by BIC. The residuals here, although they do fail the Box-Young test, they do appear to be very much white noise from our ACF plots, and the system frequencies aren't great, but they are somewhat representative of the system frequencies that are in our realization. So we can do better. We can definitely do better. Next up, we're going to try a little VAR model. So typically, this is how we would do things at work. We would definitely like to add well thought out lag variables. In this case, we're going to use the last week's panel sales and the last year's panel sales, in addition to the last week's transaction count and the last year's transaction count. We're going to add time so that we do get serially correlated residuals, and we're also going to add a categorical predictor for the day of the week. So doing that first, modeling the linear process as a regular linear model, we're going to look and model the residuals of that and see that fits the 6-1 very well, an ARMA 6-1. By now combining that process together with the exogenous variables, what we've actually created is an ARIMA X model that takes into account the 6 lags, the MA1 component, and then all of the different variables that we've introduced from the exogenous perspective. So the 4 different lag variables and the 6 different dummy variables, the reference variable being the intercept being Monday. We see the high value for the intercept here, which is making a lot of sense. And then X6 through X11 are adjustments to that intercept based off the categorical predictor that we have in here. So Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday are all going to have negative adjustments to that intercept. Again, we fit the residuals of this final ARIMA X model and we see that our correlations here appear to be white noise. The residuals look very good. Again, it fails the Box-Young test, but what doesn't? Model selection for the neural network, again, very similar to the process that we went through for the VAR model. A lot of the same setup. Again, keeping in the same regressors. It's not clear why the lags are actually being applied to the regressors here. I don't think that actually should be the case, but it was hard to play around with this model given the fact that it takes so long to train and we have so much data. So we use a little bit of a subset of the data to get this thing off the ground. Again, taking the residuals and modeling the ACFs and PACFs, it still looks like we still have some work to do here on our modeling. Forecasts. The forecasts for the seasonal model are always going to be very consistent. Recall that this model is actually predicting off the difference data. So although it looks to not be capturing a lot of the behavior, it actually is capturing quite a bit of the behavior. It's just not capturing a lot of the anomalous behavior. So again, simple model to train, not a great ASE, but again, simplicity sometimes does dominate. Forecasts for the VAR model were excellent and incredibly matched to the realization. Very low ASE. Again, it was a little bit harder to construct this particular model, a lot more legwork and sweat in order to get the data set into the format that it needed to be in order to get this to work. But it was worth it when it did work, because again, this has an excellent ASE and fantastic mapping to our realization, potentially overfit. Again, neural network, same kind of deal. We used the same setup that we used for the VAR model. Much easier to figure out what the parameters were here. Of note, when we were letting the neural net search for its own parameters, it never converged. So forcing it at lag 7 was the only way to get it to work, so we did that. The ensemble method was basically an average of letting the MLP basically use a lag 7 and a lag 1, taking all the same regressors, taking all the same stuff we use in the VAR model, and then taking just an average, a straight up average of the two predictions, and using that as our actual prediction. That improved on both of the, that was better than the neural network by itself, and it was better than the VAR model by itself. So investigating those two things further would really be where this analysis should go. The conclusion here, again, the Aruma model and seasonal model had long, all of them had long prediction horizons. Clearly, the fact that this was weekly data made the analysis very straightforward. The neural net was great to use, but very, very cumbersome to train. It was hard to get any kind of real good parameter optimization or hyperparameter tuning. Ideally, we could do some more combinations of VAR models and neural networks and play around with the different combinations of lag variables and neural network hyperparameters. Getting those two things in line and actually getting a pipeline for that would be great, and I think we could really even make more of an improvement on what we've already got, which is already pretty good. So thanks for listening. Hope you enjoyed, and see you on GitHub.